mathematicians, here are your notes for 5.1.1, so that means there's 2 days of this, and we're going to be talking about slope. So, if I say, what is the slope of something, I would like you, for the bell work, to define that word in your own words. So, what does slope mean? I'll give you just a minute here. Alright, so you could have put a number of things, and whatever you put down, as long as it makes sense to you, is probably okay. I like to think of slope as how steep something is. So if you think about the slope of a hill, that would be how steep the hill is, how fast you're going to roll down the hill if you trip at the top of it, the basic stuff. So today's goal is to be able to define a little bit more rigorously and then be able to calculate what slope actually is. So before we get started, why is slope necessary? Let's start off with a real world example. Road signs like this one indicate the grade of a road or its level of steepness. If grade is measured as a percentage, write 8% grade as a fraction. And why is this information useful? Well, just as you would suspect for 8%, what 8% means is that the downhill steepness is going to decrease 8 feet each time you travel 100 feet. So if I draw a hill, in fact, I'll just take the one out of the picture there, that when I have traveled 1,000 feet, I guess I should have put that technically up here, but when I have traveled 1,000 feet horizontally, my steepness, the amount I have gone from at the top to where I end up at the bottom of the hill, is going to change by about 8 feet. So why is this information useful? Well, in this specific instance, truck drivers need to know how steep something is in order to know what gear they need to be in on that hill. It can be very dangerous for truck drivers to go down steep hills without being exactly aware of how steep something actually is. So in this case, this is a safety issue. However, slope isn't just the grade of road. It isn't just these road signs. It has a lot of applications that we will eventually get into. So let's look at this a little further. Take a quick minute here and fill out the what I think. I know we define slope up above, but I would like you to either use my definition or the one that you brought from up above, and then go ahead and see if you know what positive and negative slopes are as well. You can go ahead and draw a picture of those if you prefer. Alright, so hopefully you paused the video, took a minute to do that. If not, you can go ahead and do that now. Again, I'm just going to go ahead and copy right in here. How steep something is. Again, it does not have to be exact. You could also say the steepness of a line if you wanted a different definition. Again, as long as you understand that slope is how the change something goes through up or down. Positive slope. Whatever you said for that, again, leave it. We just want to fill out this part. A positive slope is something that increases in both the x and the y direction. So if I were to draw a picture, I would start at the bottom left corner and go up. Up, up, and away indicates a positive slope. Another name for a positive slope is called direct variation, which basically means as x increases, so does y. You might see this also referred to as direct variation. In fact, we're going to look into this in more depth in the next lesson because there's a lot that goes into that specific idea. Moving on, however, a negative slope then makes sense that if we started at the bottom and went up, a negative slope starts at the top and goes down, meaning as x increases, as we go further right, instead of increasing, y is going to decrease. So I should have put x in here. As x increases, y decreases. And this is called indirect variation, We're not going to talk about that one as much, but it also has quite a few uses. So before we get into actually being able to calculate, we also need to know ways we can express slope. So the first way that you're going to see slope expressed is as the letter m. We use this variable to indicate that slope is changing. Eventually we will use the formula y equals mx plus b, and whenever you see m, again, you're going to recognize it as slope. The second way we can think of it is as rise over run. That's kind of a mouthful. Meaning that we always look at how much something is going up or down, and we divide it by how far something is going left or right. Next up, we can look at it as the vertical change. Remember, delta is the symbol for change, so vertical change divided by horizontal change. And that says the exact same thing as rise over run. Some people just prefer to use different vocabulary. The last one, and one of the most important ways we're going to learn how to express slope, is as the formula for slope. y2 minus y1 divided by x2 minus x1, where x1, y1 is your first coordinate and x2, y2 is your second coordinate. So if you want to put that over here in parentheses, you go right ahead. x1, y1 is your first coordinate, x2, y2 is your second coordinate. So let's go ahead and use that. The first example says use the graph at right to determine the slope of a line. Well, the first thing I would say is that I could either find these coordinates and use my formula, or what I like to do when I have a graph is I just like to be able to figure out what the rise and run are visually. So if you look here, each of these goes by 1. My rise from this point up to this point is 1, 2, 3 squares. So my rise is 3. My run, or my horizontal change, is 1, 2, 3, 4, 5, 6 blocks, or units, whatever you prefer to call them. So if I were to put that into the formula I was given up here, my slope, my m, would equal my rise, which was 3. I went up 3, positive, and I went over positive 6. I'm just putting those in there so that you notice we've got a positive and a positive, and when I put them into the formula, I get a slope of 3 divided by 6. I can reduce this and write my slope as 1/2 as well. Now, why can I do that? Well, you'll notice that if I put my slope of 1/2 on this picture, if I go up 1 block and over 2, that point is still on the line, and it's still going to lead me to my second dot. So it's totally okay, and actually I will eventually expect you to reduce your slopes to be more accurate. I also want to show you what this looks like with this formula, however. So if I find my 2 points, this one's at -2, -2. I'll put those over here. -2, -2. That would be my first point. My second point would be 4, 1. So now that I have my coordinates, I have my x1 and my y1 because that is my first x coordinate and my first y coordinate. And then I have my x2 and my y2, my second x coordinate, my second y coordinate. Now that I have those all lined up, I can put it into this formula. y2 minus y1. Notice I put it in parentheses so we don't mix up those negative signs. Divided by x2 minus x1. x2 minus x1. I go ahead and find that. 1 minus -2 is +3. 4 minus -2 is +6. And you'll notice that whether I do it visually using the graph or using the formula, I get the same slope of 3 divided by 6, or 1/2. All right, let's jump to the back and see that again. If you're ready, go ahead and try the next couple on your own. Otherwise, I'm going to do just another one so we're on the same page. This says find the slope of the line that passes through the points -2, -2, and 4, 1. Well, we already did that, but I want to show you again. Let's even find, I'm going to pick, oh no, I'm just going to leave those alone. My apologies. I thought I had chosen different points for that. But again, if you don't have the picture, it is completely possible to use the formula, just as I showed you over here. I'm not going to go through this problem again for the sake of time. If you want, you can rewind the video and watch it again, but I'm actually going to jump over to that second example. So find the slope of the line that passes through 3, 5 and -1, 4. So as I'm starting these, before I am really confident with what I'm doing and confident with the formula, I like to label each part of my points so that I'm not mixing anything up. I think this is a good idea for all of you starting out. If you don't want to do this, you feel comfortable, you don't have to. It can just be helpful. And then I remember I do rise over run, which means the y's are on top. Again, with anything math, I like y1 minus y2 over x1 minus x2. I like to write out my formula. My formula in this case was on the other page. So if I bring it over here, works too. Notice, on the other page, I said y2 minus y1 over x2 minus x1. On this one, I flipped the first and second coordinates. The cool thing about this formula is it works no matter which one you use, as long as your 1's are lined up in one column and your 2's are lined up in another column. You can do y2 minus y1, x2 minus x1, as long as they're lined up. That is all that matters. I actually tend to switch mine around quite often, but I ultimately know that my formula says the y's are on top, the x's are on bottom, and I'm just keeping everything aligned. All right, enough about my idiosyncrasies. Let's start plugging things in. y1 is 5 minus y2, which is 4, divided by x1, which is 3, minus x2, which is -1. I'm going to throw that in parentheses so I don't miss that negative. And then we simplify. 5 minus 4 is 1. 3 minus -1 is 4. So my slope is 4. Again, as we're getting used to these, I want you to get used to using m as your variable. So when you write your answer, go ahead and write m equals 1/4. Let's keep going here. Find the slope of the line through those points. If you don't want to replace them, you can still just label them up here. x2, y2. I happen to use my formula from up above, so I don't rewrite it, but y1 is 3 minus y2 is 1, divided by -5 minus 2. 3 minus 1, 2 over -7. Final answer, m equals -2/7. Just like that. All right, last one here, challenge problem. A store sells sugar in bulk for 25 cents per pound. Using what you know about slope, graph the relation, and then draw a line through the points on your graph to find the slope. So we've been making a lot of tables, and often when I don't have a lot to go on, that's my first thought, is let me go ahead and make a table to see what this looks like. So if this is pounds on top, and this is money on bottom, it says 25 cents per pound, so 1 pound is going to be 0.25 of a dollar. If I want 2 pounds, it's going to be 50 cents. If I want 3 pounds, it's going to be 75. And if I want 4 pounds, it's going to be $1. So what I've done here is essentially made a table. But another way to look at this is as a set of ordered pairs. 1, 0.25, 2, 0.50. and so on and so forth. And you can look at this as a relation. So when I go over and I graph this, as I've been seeing up to this point, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, I'm going to make my tick marks on my y-axis go up by 0.25, not by 1 like they are on the x-axis. It's just a personal preference so that it graphs a little bit easier. And then 1 pound, 2 pound, 3 pound, 4, 5, and etc. So as I'm graphing this, 1 at 0.25, 2 at 50, 3 at 75, you're going to notice this pattern. And it's going to be a linear pattern, as I've mentioned. So if I draw my line through here, it's kind of hard to see the points when I do this. What this line indicates is that I could buy any amount. It doesn't necessarily have to be whole pounds. And there would be a number in between that I could pay. So if I wanted exactly halfway in between 1 and 2 pounds, if I wanted 1.5 pounds, there would be a price in between that I could pay. I don't have to necessarily do it in whole increments. So if they're discrete numbers, where they're all individual dots, that means you can only buy them in whole numbers. However, because we've got that line, this is continuous, and now we can find our slope. However, you're going to notice it's really easy. If you're going up by 0.25 and over by 1, your slope each and every time is going to be changing by positive 0.25. So, in this case, your slope is the amount that you are changing by each time. Pretty cool. All right, practice, practice, practice. If you have any questions, let me know.